Yes, okay, so quick about me. I'm Sven Marcos. I work at TU Braunschweig for the University Library. And yeah, I'm going to talk to you about the SURESOFT project that has been running for 2 years almost now. And our goal is to move more towards sustainable research software and tackle the problems that come with that. And yes, of course, I'm not alone in this. We already mentioned that Jan is also part of this, but we have a wide range of researchers from different disciplines um, who are participating in this project. We have people from acoustics, from operating systems research, communication technologies, computational fluid dynamics, chemistry, the library, of course, and also our local IT center at TU Braunschweig, who help us out with some infrastructure. And what we have in common is that we all have to develop research software in some way, and are therefore, of course, interested in making it as sustainable as we can and as sustainable as possible. So before we really start out, let's have a quick look at the outline of this talk. I'm going to start with a quick motivation. Why is software sustainability suddenly a topic for us? Why is it even important? And then I'll move on to our approach and how we want to deal with the problems, how we want to try to solve them. And then I'll introduce you to the workflow we hope to end up with by the end of the project that hopefully helps us solve some of the problems we face with sustainability. And then I'll end with a conclusion, and I'll give you a quick outlook onto our future work. So, about the motivation, why is software sustainability a topic suddenly, or more or less, not suddenly, but it has been for a few years now. But there is this pretty famous survey, at least in our circles, where researchers were asked how they deal and how important developing and using software is to them in their daily work. And 84% of the participating scientists said that, yes, developing software is an essential part of their work. But while the software itself is getting more important in the scientific process, there have also been a large number of publications that had either incorrect results or results that were difficult or even impossible to reproduce by other scientists. And this has led to articles like the one on the right that asks the question, is there a reproducibility crisis in science? Where quite a large number of scientists said, yes, we do have a reproducibility crisis or even a credibility crisis in science. So now the question is, how did we get here? Why is this? Why do we have these problems with our software? Is there data we can't reproduce? Why do we have this problem with quality? And there are several reasons for this. Some of you may have heard already. The first one being that usually scientists and researchers are self-taught software developers. They never received any kind of formal education in the principles and practices of software engineering in their college studies. And another point is that they don't gain any reputation for developing software. The only thing that matters to them is the data that is generated by the software, but the software is not considered to be a part of the scientific output and result itself. So it's only considered to be some kind of advanced calculator that spits out some results you can publish at the end. So while we're speaking about publishing, there's also this rather prominent publish or perish mentality that we have in science, and we are pressed to publish results as fast as possible because our reputation is entirely built on the papers we publish and the citations and how often we are cited. And if we have this time pressure, we of course don't have the time to properly design and test a good software system. So, and this of course leads to some consequences. There are some common problems that research software faces that we especially want to tackle in the SURESOFT context. The first one being low code quality that often comes with research software. We've just talked about how scientists are not educated in the ways of software engineering, and that we have very hard time constraints when we develop this software because only the results matter to us. So this, of course, can lead to a low code quality, which makes it hard to understand the software, maintain it, and fix bugs that we may have introduced. And then also it makes it harder to extend the software for future use cases. And since we already also talked about how the software is not considered to be a part of the result of our research, it is often also not published alongside our paper with the data. And since nobody else is going to see our software, there's also no real incentive to document it. And this can, of course, lead to some problems. Imagine the next generation of researchers needs to pick up some old piece of software and extend it to some future use cases, or they found a bug that they need to fix, but they have a really hard time trying to understand what's going on inside the software because there's no documentation at all. And then there's another property of software to consider. It really often depends on other external dependencies like third-party libraries, a specific runtime environment, so to speak, which may not be available to other researchers. So let's come back to the next generation of scientists who maybe want to pick up some old piece of software. And maybe the libraries the software depends on are no longer available on the internet, or at least rather hard to find. Or even if you publish your software so that other researchers can try to reuse it, the dependencies may not be available to them. And this, of course, means if they don't have the necessary dependencies, they cannot execute the software, which in turn implies that they also cannot reproduce the data you've published alongside your paper. So with these reasons and consequences in mind, we can try to find a definition of software sustainability that fits our use case. And for us, this comes down to three essential criteria. The first one is reproducibility, what we've already talked about. You want other scientists to be able to reproduce data using the software we've written and reproduce the data we've published. So this, of course, implies that the software needs to be available to them, including the runtime environment necessary to execute it. And there's also the point of endurance, a term you've also probably heard already at this conference at some point. So we want our software to stay useful over time. We want it to still be able to do what it needs to do in a couple of years. And we want to be able to maintain it and fix bugs and still use it later on. And then there's also the point of evolvability. Science is not a static thing. We move forward. The scientific process is moving forward, and maybe we need to adapt our software to use cases we couldn't foresee in the past. So our software needs to be flexible enough so that we can evolve it to fit new use cases. So we've defined what software sustainability means to us, but how do we tackle the problems? How do we get there? And this is where our approach comes in. And basically, we are trying to build our project upon two pillars. The first one being education. We've already talked about how scientists lack the proper software engineering skills usually to write high quality software system. And of course, they also need to learn how to document their software properly. They need to learn how to apply proper software engineering principles and how to properly test their software. And this is why we intend to have interactive workshops where scientists can follow along some code examples maybe. And we've already tried some of them out in the context of another institution we have at TU Braunschweig, the Musen Center, where we've already given some talks about software engineering principles and things like test-driven development. And another part we have to consider is the infrastructure and the methods we need to ensure software sustainability. And in this part we want to consider things like technologies that can help us to ensure that software stays available, that other people can find it and reproduce our data. And we'll have a look at this part in greater detail first. The first technology we want to use there are container technologies, and I assume most of you are familiar with them. If not, basically they enable us to encapsulate an entire runtime environment, including the application and the dependencies it needs. And they are easily shared and reused. So if another scientist runs an experiment with the container you created, they will be able to reproduce the exact same results you generated in the first place. You may have heard of Docker, which is the most famous container technology, but we also plan to use and have already used Singularity in our context, which is another container technology which is tailored more specifically towards the scientific computing workflow. It integrates very easily with technologies like MPI and CUDA, so it's a very good candidate to use on high performance computing clusters, so you can get everything you need, the entire software stack you need onto these clusters, and run your application there. Then let's move on to version control systems. And maybe you are asking yourselves now, why are we talking about something this basic? Everybody knows Git nowadays. Everybody uses it. Why is this even a topic? But unfortunately, we've heard horror stories of scientists zipping up their source code and sending it around in emails, which of course resulted in everybody having a different kind of copy of the application, and nobody had an idea what the application could do and what the current state of the software was. And this is why we want to establish the use of version control systems more in software engineering, in research software engineering. If you aren't familiar with them, a quick summary, they can track and manage the changes we make to our source code, and you can commit those changes to the version control system. And they, in case of Git, they receive a unique identifier called the commit hash. And those commits document the changes you've made to the software over time. And of course, if something goes wrong, we can roll back to a previous change if, for example, we messed something up in a newer change. And this can help us, of course, a great deal with maintainability of our software. And of course, if we combine the version control system with the centralized repository hosting platform like GitLab, for example, that we use at TU Braunschweig, this, of course, helps multiple developers with collaboration. Then let's have a quick look at continuous integration, which is a development practice which builds upon the use of version control systems, which is something we also use already to quite successfully. And you can see the entire workflow of continuous integration more or less in this graphic. Starts here on the left, where a developer changes something in their software, and they compile and test it locally, and everything went well, they commit their changes to the main branch of the repository. And there it's usually picked up by a continuous integration server that builds and tests our software in a production environment. And if anything goes wrong during these tests, the continuous integration server will notify the developers, and so they can drop everything they are doing and try to fix the bugs as soon as possible. In the context of scientific computing, there's of course some unique challenges to continuous integration. For example, some of our tests may be so computationally intensive that it's not feasible to run them on a simple continuous integration server. And this is why we also need some integration with high performance clusters. Something we've already established at TU Braunschweig. For example, we have successfully used technology called Jacama CI, which is a custom runner for the integrated GitLab continuous integration service. We've also used a homegrown solution called HPC Rocket that is independent of any specific continuous integration platform. There is another thing I want to highlight about continuous integration. There's a common misconception about this practice. Most people assume it's about this continuous integration server that picks up your changes and builds and tests it automatically in a production environment. But that is not entirely true. It is important. It is very important. But if we have a look at the name of the practice, it says continuous integration. Integration is in the name. And this is why this committing to the main branch of your repository is a very important part of this practice. So imagine you have multiple developers on a project and they all are working on different branches of their repository, and they make changes, but they never really merge these changes together until quite a short time before they want to release the next version of their project. And now they try to merge this all together. And it's going to be really hard to get these diverging software versions together because, yes, the software has diverged by so much that it's not obvious how to get it all back together. And if something then goes wrong in the test cases, it's not easy to identify where things went wrong. And this is why it's important to regularly commit to the main branch of the repository. So the change set of the integration stays really small. And if it stays small and the test fails, it's also very easy to identify where the errors happened. So this is why this is such an important part of continuous integration, but it's very often not considered when this practice is employed because people only see the automation part of the practice. Then let's move on to continuous analysis, which is an extension of continuous integration. And the main idea here is basically that you run your continuous integration pipeline inside a container. And this container, of course, has to provide the necessary runtime environment to compile and test your application. So whenever some developer commit their changes to your repository, the CI server will pick it up, compile and test it inside the container. And now the idea is that you extend the container you have used to compile and test the application with the compiled software, and you upload this container somewhere so that other scientists can reuse it and download and reuse it to reproduce your application and your computation. And of course, reproducibility with this approach is pretty much guaranteed because you've used the exact same runtime environment just before in your continuous integration pipeline to test and compile your software. So it's exact same runtime environment. So this can help us a great deal with reproducibility. And then there's also, of course, the publication and archiving part to consider. We've already established that we not only need to publish the data that our software produced, but it's also important to publish the source code as well as the compiled executable with its runtime environment that's necessary to execute it. So that other people can understand from the source code what's going on in your software, how you even got to these results. And of course, they can then use the runtime environment with the software to actually rerun your computation. But when we publish our software, it needs to be published in a dedicated archiving platform that is accessible to other researchers. And there we need to consider the FAIR principles. You are also probably familiar with those. For those who aren't, it's an acronym of findable, accessible, interoperable, and reusable. And this basically means to be findable, our software needs to be provided with a unique identifier and some metadata, so it can be found on your repository and also be cited. Accessibility means in this case that your repository needs to be accessible by other researchers. At least they need to be able to try to access the software in some way. Interoperability means that we need to be careful of which kind of data formats and file formats we use, so that we aren't locked into proprietary solutions and everybody can try to interface with your software or data in an open way. And then, of course, there's also the reusability to consider. And this means that we also need to provide a proper license for our software, a license that allows other researchers to even reuse the software. All right, then let's move on to the educational part, the second pillar of our SURESOFT approach. And we've already talked about just now in the publication part, and even earlier, that we need some form of documentation and metadata for our software so that other people know how to install our software, how to run it, what our software is even about. And this is why we need to teach our scientists how to properly document their software, how to explain the important concepts they've used in their software. And then there are, of course, also the software engineering principles that, scientists often aren't familiar with. So, for example, we've already had workshops regarding the solid principles and design patterns. And we intend to even build up more workshops in this direction and teaching more basic concepts of software design, like concepts like coupling and cohesion and so on. And then our scientists also need to be able to test their software, a concept that most scientists aren't familiar with yet. And testing the scientific software is also not always trivial, right? Imagine you have some hardware-dependent computation, or you are running a numerical simulation that has some accuracy requirements or something like this. We also have already worked on and held a workshop about test-driven development. If you aren't familiar with it, this is a practice where you write a failing test first before you even implement the functionality in your application. So you start with a failing test, then you build the functionality into your application. And if there's something to clean up, if there's something you could improve about your design, you do that in a third step. And you repeat this cycle until the software does what it's supposed to do. And this, of course, means that you eventually end up with the software that is pretty much entirely covered by tests. And these tests can, of course, also serve as a form of low-level documentation, because if another scientist has a look at your tests, they will find a test case for pretty much every use case of your application. So tests can also serve as a form of documentation. And then, of course, we'll also teach the practices and technologies I've talked about previously, like version control, continuous integration, containerization, and how to manage research data and what kind of files and what kind of file structure we need to have to archive our software properly. And then, of course, we also need to talk about software licensing to enable other researchers to reuse our software. So let's assume our scientists are all very educated in the area of software engineering now. And then this is a kind of a workflow we hope to end up with by the end of the project. Look at the bottom right, this is where it all starts. We may have some academic software developers who develop their research software and they commit their changes to a version control system. And as we've discussed earlier, this version control system should be connected to a continuous integration service that picks up the latest changes and builds and tests them. And as it is with our scientific use cases, we may have some kind of test that requires more computational resources. So it's necessary to be able to trigger a high performance computing cluster from inside the CI pipeline. And this cluster needs to report back the results of this computation. And if everything went well, we can use the continuous analysis approach we discussed earlier to create new containers and upload this to a connected container registry where other researchers can download it and rerun our experiment or use our software to run their own experiment. And if we want to archive some experiment, we need a dedicated publication and archiving platform. And in our case, we want this platform to be connected to a continuous integration service as well. And this continuous integration service is supposed to rerun the experiments you want to archive and ensure that the data is reproducible. And only then we are going to archive this software. So I told you this is the workflow we hope to end up with at the end of the project. And we have a pretty good grasp on the right side of this diagram already. We have a university-wide GitLab instance that is available to all members of TU Braunschweig. You also use the built-in continuous integration service, GitLab CI. And I've told you about the technologies we employ to run our tests on HPC clusters like Jacama CI and our homegrown solution, HPC Rocket. We also are connected to an image repository, to a container registry, where at least members at TU Braunschweig can for now download and reuse our containers. However, what is still a work in progress, when we have the publication platform in place, the archival continuous integration service is still something we need to have a look at it in the future, because determining when a project or experiment is reproducible is not always trivial. Imagine a workflow where you have such a large amount of data that it's not feasible to upload it. Imagine multiple terabytes or something. And now, if you only publish your software, upload your software, but not the data, how do you determine that the experiment can be reproduced successfully? And this is something we haven't figured out ourselves yet, but we hope to end up with some basic solution for this by the end of the project. So you've seen the workflow, and of course we didn't just come up with this workflow. This workflow has been developed and has been established with few projects, with 5 projects to be specific. We have El Paso from the area of acoustics, and Simone from the area of communication technologies, and virtual fluids is a CFD application, and PyADF is a quantum chemistry framework. And we've also have Themis, which unfortunately doesn't have a logo yet because it's rather new and came later on in the project. It joined in later, and which is a Byzantine fault-tolerant framework. And we've all been using this workflow rather successfully so far. We've while most of us had version control already in place at the beginning of the project, what we ended up adding then was a continuous integration pipeline that was specifically tailored to each of the projects. And we've also been able to run more computational intensive computations on or tests on the HPC clusters at TU Braunschweig from inside our CI pipeline. And the container registry is also currently being tested if we can employ continuous analysis properly. And it's all working out quite well so far, except of course for the archival continuous integration, where we try to reproduce experiments because of the problems I mentioned earlier. So then let's come to the conclusion. I've introduced you to the SURESOFT project. We've been up and running since 2020 with 5 different software projects I just introduced to you from different fields of science to get a unique perspective on the requirements of sustainability. And yes, we've started establishing and using the workflow I've introduced to you and the infrastructure we've provided to TU Braunschweig. And we are currently also developing a policy for sustainable research software at TU Braunschweig to help guide others research software developers and projects in the right direction when they want to join in. And then we also held some workshops already, but we also plan to expand this a bit more about workshops about software engineering principles and the modern tools and technology I've talked about. And we'll probably start within our research group, and if everything works well, we'll expand this to the whole TU Braunschweig, and then of course into the entire research community to share what we've learned in our endeavor. And yes, that is it from me. I hope I've caught your interest at least a little bit. And if you have any questions, feel free to ask them.